Okay, today we're going to be continuing in 5.1 when our goal is to use fundamental identities, and we are going to continue just practicing verifying the identity algebraically. Remember that when we do this, we only work on one side of the identity. We don't work on both sides and meet in the middle. We choose one side to start with and make it match the other. It's good to start with usually the most complicated side. And so we can see what we have in number 1. And it's pretty obvious that the left-hand side is the most complicated side. So one thing, they're already in terms of sine and cosine. Sometimes it's handy to get a common denominator. And so essentially what we're going to do in number 1 is multiply this side by cosine theta over cosine theta. That fraction, I should say. And we can multiply this term by sine theta over sine of theta. Okay, so what we'll do is we'll work on the left-hand side. So when we do that, we end up with sine theta cosine theta plus cosine square theta. And then essentially we'll just kind of feed two birds with one feeder here. We'll subtract cosine theta times sine of theta. And we'll subtract negative sine theta times sine theta. So the two negatives will make a positive sine square theta. And now that's all going to be over the common denominator of cosine theta sine theta. So notice that this sine theta cosine theta and this negative cosine theta sine theta, these cancel. So we're left with cosine square theta plus sine square theta over cosine theta sine theta. And look, one of our trig identities, cosine square theta plus sine square theta is 1. And so we have 1 over cosine theta sine theta. So this would be the same thing as saying 1 over cosine theta times 1 over sine theta. Just breaking that up. And this gives us secant theta times cosecant theta. And that's what we wanted. So remember, the last statement should be that identity. And that, yes, we verified that that identity is true. Okay. Let's move on to number 2. We have the natural log of the absolute value of 1 plus cosine theta plus the natural log of the absolute value of 1 minus cosine theta. And somehow we need to get that to equal 2 times the natural log of the absolute value of sine of theta. Whew. Well, remember that the thing with logs is that we have properties of logs we can use. When we're adding two logs, it's really like multiplying the arguments. So I really want to multiply the 1 plus cosine theta and 1 minus cosine theta together. And if we do multiply those, that gives us 1 minus cosine square theta. And that's one of basically the corollaries of the trig identity. We know that if sine square theta plus cosine square theta is 1, then 1 minus cosine square theta is sine square theta. And remember that you wouldn't really need to write this step, but remember that sine square theta is really like sine of theta squared. And when we have the properties of logs say that in the argument, if we're squaring something, or if we have an exponent, that we can bring that out front. And look, we have what we wanted. We have 2 times the natural log of sine theta. Okay. Again, this step, I wouldn't need to see that step. You can jump right from here to here. But I just wanted to remind you about that that's really what sine square theta means. Okay? So another tactic to help us out is to factor. And we're going to factor the expression and then use the fundamental identities to simplify. So if we look at number 3, notice that we have a secant square theta in both terms, or secant squared x in both terms. So I can take out a secant squared x, and I end up then with tangent squared x plus 1. Thinking about the Pythagorean identities, notice that tangent squared x plus 1 is the same as secant squared x. And look, these are the same. They're both secant squared x, so secant squared x times secant squared x is going to be secant to the fourth x. And that's pretty much as simple as it can get. We wouldn't want to turn that into 1 over cosine. We'd try to avoid the trig functions in the denominator when possible. And so we just use the reciprocal, okay? How about number 4? Well, this is actually a perfect square trinomial. We can factor that as 1 minus sine squared x squared. So again, it has that perfect square trinomial form, so we can factor that as 1 minus sine squared x squared. And again, using the fundamental identities, 1 minus sine squared x is the same as cosine squared x. And so then cosine squared x squared would be cosine to the fourth x. And that's as simple as we can make it. Okay? Let's keep factoring in number 5. Number 5, we have secant cubed x minus secant squared x minus secant x plus 1. Well, we've got 4 terms. That looks like an awesome time to group. So in the first 2 terms, I could take out a secant squared x. And then I end up with secant x minus 1. And in the second 2 terms, why don't I take out a negative 1? That leaves me with secant x minus 1. And I can see that I can group. So one of my factors will be secant x minus 1. The other will be secant squared x minus 1. And look, these are make up one of the Pythagorean identities. I know that secant squared x minus 1 is the same as tangent squared x. And we could think about turning it into sine and cosine, but secant involves cosine in the denominator, as does tangent. So this is going to be all she wrote. There are other ways that you could simplify if it doesn't. Sometimes these are hard to decide when to stop, not going to lie, which is why these are nice, because you can know when you're done by trying to get to the end game over here. In a test situation, again, we would make sure that these would be matching, or we would say, like, write in terms of this specific trig function, okay? But maybe some of you guys wanted to do something different. Maybe you guys saw that this secant x minus 1, well, secant squared x minus 1, maybe instead you guys wanted to write that as secant x plus 1, secant x minus 1. And then, oops, sorry, minus 1 over here. And then notice that we have this repeated factor. So you could rewrite that as secant x minus 1 squared times secant x plus 1. So like that's another possibility. So it just kind of depends on your personal preference. But that's another option also. Okay. In number 6, we have cosecant squared x minus cotangent x minus 3. Well, let's try to get them all with the same trig function. I recognize that cosecant squared x is part of a Pythagorean identity with cotangent squared x, that cosecant squared x is the same as cotangent squared x plus 1. So I'll replace that. And then I'll try to write in standard form with the squared trig expression first, the regular trig expression in the middle, and then the constant on the end. And now that it's in this quadratic form, perhaps I can factor. And I would use cotangent x and cotangent x to make the cotangent x squared. And then if we use negative 2 and positive 1, that gives us the outer inner we want. And again, this is about it. That's about all we can do. Okay? So again, notice that when we're factoring, that kind of helps us simplify things a little bit. This really gets to be important in 5.3 when we factor in order to help solve equations. So that's one reason that we're kind of leaving it open-ended as far as the factoring is concerned. Okay? All right. So let's, again, just practice. This is all this is just practice with identities in 5.1 and 5.2. So we're going to perform this operation and use the fundamental identities to simplify. So here, what I could do is I could just start distributing. I see that the outer inner is going to cancel. and I'm left with cotangent squared x minus cosecant squared x. Now those are both involved in the Pythagorean identity that states that cotangent squared x plus 1 equals cosecant squared x. So think about manipulating that around and what would happen. What we could do is think about subtracting cosecant squared x, subtracting 1, and what we would have is that cotangent squared x minus cosecant squared x equals -1. That's essentially what that is. That's one of those little corollary things. And so we can just simplify that to -1, and that's what that expression is equivalent to. Okay. In number 8, another nice tactic is to try to get a common denominator. So we're going to multiply this guy by secant x minus 1 over secant x minus 1. And we can multiply this guy by secant x plus 1 over secant x plus 1. And so here we're left with secant x minus 1. And then I'll distribute the negative again. I have -1 times secant x, so that's minus secant x. -1 times 1 is -1. And I have that all over my common denominator, secant x plus 1, secant x minus 1. Well, I have this common denominator, but oftentimes then our numerator, things end up being a little simpler. Notice that the secant x and negative secant x cancel, so I'm just left with a -2 up top. And in the denominator, I'm noticing that when I have these, that I have conjugates, so if I multiply those together, I end up with secant squared x minus 1. And I notice that this is related to one of the trig identities. Remember, think about the fact that we had tangent squared x plus 1 equals secant squared x. So what is secant squared x minus 1? Well, that would be tangent squared x. I wrote too big, sorry. So I can change this here to tangent squared x. And essentially what this is, and again, I wouldn't need to see this step, but this is the same as -2 times 1 over the tangent squared x. And what is 1 over the tangent squared x? Well, that's just cotangent squared x. And so that would be my simplified form, -2 times cotangent squared x. And again, you can jump right from here to here with those reciprocal identities. I'm totally okay if you have one of them in the denominator to put it in the numerator using the reciprocal identity and vice versa. I don't need to see that step unless you find it helpful. Example 9, we want to rewrite the expression so that it is not in rational form, in fractional form. So we're going to try to get rid of those pieces from the denominator. Oftentimes, a good way to do that is by using the conjugates. Notice in these fractions when we created common denominators, like here they were conjugates, and when we multiply those conjugates together, sometimes we get something that's pretty special. So that's another tactic that we can use, is to multiply by the conjugate to get, to see if something pops up from that. So I can multiply everything by the conjugate of the denominator, which is tangent x minus secant x. And so in the numerator, I'm just going to leave this factored, 5 times tangent x minus secant x. And in the denominator, I end up with tangent squared x minus secant squared x. And once again, if we think about that, that's part of one of our identities. And if we thought about manipulating that around, tangent squared x minus secant squared x would end up giving us -1. I'll just work across here, sorry. So that gives me -1. And now that that's -1, I can totally eliminate the fraction. Now I know that this is -5 times tangent x minus secant x. And now this is not in fractional form, so we're all set. All right. So another thing is, I'm just trying to get through this so you can start on your work, is to use trig substitution to write the algebraic expression as a trig function of theta. and then where theta is between 0 and pi over 2. This ends up being really helpful later. So let's substitute that in. We're going to put in place of x, we're going to put this 2 sine of theta. So again, we just replace the x in this expression with the 2 sine of theta. And essentially, that makes 4 times sine square theta. Because we need to square the 2 and we need to square the theta. So then this makes 4 times 4 is 16. So then the next expression is the square root of 16 minus 16 times the sine squared of theta, or sine theta squared. And notice that we can actually factor. We can factor a 16 out, and that leaves me with 1 minus sine squared theta. And here we go again. This is another one of those identities. What is 1 minus sine squared theta? Well, again, we know that sine squared theta plus cosine squared theta equals 1. So 1 minus sine squared theta really is cosine squared theta. And now, essentially, we have 2 perfect squares that are under the radical. So we can take the square root of 16, and that gives me 4. And then we want to take the square root of cosine squared theta, which essentially is cosine theta. And we have the absolute value because we want to make sure that it's positive when we take the square root. However, this is where this domain comes into play. If theta is positive, I don't have to worry about this being negative at all. So in my final answer here, because of the domain, I don't need the bars. And I can just say that that equals 4 cosine theta. So that's something kind of fun. We can substitute a trig expression in, use the fundamental identities to simplify, and it ends up being something kind of fun, 4 cosine theta. The next thing we're going to do is use a graphing calculator to solve this equation for theta, where, again, theta is between 0 and 2 pi. And so we're going to want to put, so we can use our graphing calculator, so we can get those out. So you guys, if you want to get the graphing calculator out, let me go grab mine one real quick. So we'll grab a graphing calculator. And again, that means that we're going to put one of these sides in y1, and we're going to put this other side in y2. And we can make a note where they're going to intersect. So let's just type those in. So in my y1, I have the sine of x. And in the y2, I have the square root of 1 minus, and then I have to do the cosine of x squared like this. So again, even though we write cosine squared x in the calculator, we have to tell it to square cosine x. And again, be careful that you are squaring the entire cosine function, that you're not just squaring the x. So make sure that you're cautious about the parentheses there. Now, as far as the window is concerned, this is telling us that we're going to go from 0 to 2 pi. So maybe our window could be 0 to 2 pi. I don't know, we often go by pi over 2, so maybe that would be something to go by. And then our y's, looking at these functions, they're pretty simple. Maybe we could just go from -2 to 2. And we could go by ones. Okay. So again, there's no real formal way to write the window as long as you can tell what's going on. So let's make that adjustment in the window. So we can go from 0 to 2 pi. And notice when you use the pi key, it populates all the decimals on its own. X scale is pi over 2. And then y min -2 to 2, and we're going by ones. Okay, and so now we can graph, and we can see the moment of truth. So here's the first function that is graphing, and then here's the second function. Oh, look, it's like tracing that other function, isn't it? So I notice if I'm going to draw a sketch, which we're supposed to do, I noticed that if I were to graph the sine of theta, that's looking like this, as we would expect. And when I'm graphing this other function, it's looking like this. And we know that the solution is going to be all the points where they intersect. Well, they intersect all up through here, don't they? So what we would do is to solve our equation for theta, basically it's everything from 0 all the way to pi. So our solution set would be the interval from 0 to pi. That's our answer as far as that goes. That's our solution interval, because it's not just a couple different, it's not just, you know, 1 or 2 points. It's that whole intersection piece. And that's it. So I wanted to kind of get through that so that you could practice on the homework. And that's all this is about. It's just practice, practice, practice. The more problems that you do, the more clear these identities will be for you. Okay? All right, have a good one. We'll talk to you soon. Bye.